Test. Hey, people. Yes. Welcome to this talk on runtime security. And I want to start out, this is a very, very special stage for me because it was exactly on this stage where last year, Vadim and I introduced the software bill of behavior. And 2 years ago, I was here with 3 students talking about threat intelligence. We're still on the same topic and we have progressed very much. Today, it's about the 2 big enemies of runtime security. One is in the title, and that's noise. So, and I'll be talking, everything that you can do here is also called digitally sovereign. And by that, I mean nothing political. It just means that you can do it yourself in your own data center, self-host all of this on your own nodes. First off, before I start, let's start at the beginning. I am here, yes, alone, as I'm Constanze, I'm a CNCF ambassador, but I do this together with 2 CNCF projects and work directly with their lead maintainers, Matthias and Dom. And I can only say that is amazingly grateful for how much I learned from them each single week that we work together on this huge scope of project, and that is making attack trees visible in real time. And and Sylvain, I wouldn't be here without Sylvain sponsoring me. This is the first time I've ever been sponsored, so huge applause for Ape Factory for making this possible. Thank you. Because in fact, I'm an independent researcher, and that's sometimes a bit hard to get funding for. So what are the big problems in runtime security? So there are 2 options that you pretty much have. You either configure your rules too loosely, and that means you see nothing. Or then you turn it up, and suddenly you see everything, and you've got noise without end. And this is exactly the problem I want to achieve by making, or I want to achieve more accessible runtime security, meaning allowing people to have a little bit of leeway, not necessarily misconfiguring, but maybe having the I don't know approach and still achieving good enough runtime security. Because the thing is that at the moment, if we think about UpArmor, LSMs, etc., they have about an adoption rate of 1% in the Linux ecosystem. And I want to get it to somewhere close to 90%, that everybody has at least a chance to start somewhere. And this is why we have to also discriminate between the things that we know. And I'm going to give you that metaphor. Last year, I talked about what's the difference between SBOMs, what do they cover? So if we had a container, and you imagine it's a pharmaceutical package, the SBOM is the ingredients list. And the SBOM basically was motivated by SolarWinds loosely. Executive Order Joe Biden in 2021 enabled the first time that we have these curated lists of everything that goes into the software. And that gives us the ability to have a transparent inventory that we can search at runtime. But search is the key point. We need something to search for. And what we typically search for is CVEs. Those are lists in threat intel or vulnerability databases or VEX documents. And now this is the question, what kind of attacks do not have CVEs? So one thing is there's a Datadog study here that apparently 54, I was shocked by this, people still expose their Kubernetes clusters to the public. That's one problem. Then we have increasing reports of identity portals directly being hacked, and all other kinds of very difficult to attribute token theft and identity theft. Also think about phishing, also very, very hard to attribute in cloud native. And the key here is that if you have the key, you don't need a CVE, right? And it's extremely hard. And yeah, and it rhymes. And the other point is, like, I think Liz Rice said it, you can't scan yourself secure. So an SBOM, everything is that great. Like LSMs are great if you use them. Immutable, whatever, is great if you have it. It comes at a price. And this is dealing with the rest of the risk that we have at runtime. And of course, you've probably heard of Mythos is too dangerous to be released to the public because it finds 0 days. Believe it or not, but definitely AI-assisted 0-day finding is getting more and more achievable. I can say that from my own research. Building exploits, if you know what you're doing, has gotten extremely fast. That helps us as defenders as well, but this is also something by definition a 0-day is not in a CVE database, and the same thing for your first-party code, right? You'll likely not see that in a database either. So what do we do with the stuff that we don't have records in the threat intelligence, what we're looking for? And now this is the thing that I want to talk about today as well, is what do I mean by too many alerts? This is, we're going to come back to it, 150 seconds of alerts, slightly misconfigured profiles here. So you see 14,000-ish alerts. That is definitely not the thing that you're going to look at manually and chase down. And by the end of the talk, I hope that I can convince you that this is something that within purely deterministic algorithms, we can actually narrow down to the things that are relevant. And yeah, because one of the biggest problems in runtime security is storing that evidence today for the attack that might happen in 6 months. And if you have ever stored HTTP logs, you know how big they are, and that you, not instantly, but very quickly run into petabytes of storage solutions with all the problems that comes in maintaining your storage cluster, keeping that performant, etc. And then you're throwing away the stuff, and then you don't have the evidence. But this is a problem all this time. And the question is, what if we were able to, on the node directly, pre-filter, pre-correlate those alerts that I just showed you, those 14,000, and only take about 10 records per each incident out and give it to the human to look at what we think this is actually a relevant alert that you should look at and investigate it and not look at those 14,000. And yeah, at this point, I come to the explanation of what goes in here. I said I'm using 2 CNCF projects. One is Kubescape, an incubating project, and one is Pixie. So when I say Kubescape, I want you to think about a vertical filter of any point in time that filters coarsely everything that comes in, deduplicates it, and checks if there is a big problem, a very big signal in somewhere in the cluster that we can grab for. And what we choose to use for this is that bill of behavior thing. So the way we operate it, and it's scalable for many nodes, is we have a daemon set that runs inspector gadget under the hood in each node, and we have a singleton pattern that is stored once where we sign all the rules and basically the interpretation of that rule. So what actually does this SBOB contain? So if you've ever worked with any of the security profiles, typically they're very low level. We try to make it, pull it into a YAML and make it as recognizable to any of you as possible by using stuff like endpoints that you know from network policies, arguments and executables and arguments, capability sets, and down here the endpoints, the DNS endpoints that resolve to certain IP addresses. So I hope there's nothing in there that you haven't seen as an engineer. And the idea is, can we get it down to approximately 100, 200 lines of YAML code, sign it off, and that be enough for that vertical filter for each app to have? And here's the important point, do it from the person who understands the application. That's the big difference from learning your own profile on your own cluster. That has the problem. If your attacker is already in there, then you're learning the attacker behavior as the normal behavior, right? And typically also, if you do this with eBPF, those profiles, is there anyone from Dynatrace? So I did one agent once was 120,000 lines of eBPF profile. So, and that also has significant consequences on performance if you were to diff that in real time the whole time. So and the idea here is make it accessible by saying only the things that really matter. And this is where the whole wildcards thing comes in, that you can say relative paths, you can say from this path onwards, varlog Apache 2, well, whatever happens in there is probably intended, but if it's /etc/hosts, well, that's definitely not alerted. So the insight here is that some paths in the file system are much more relevant than others, and that some you can simply say, well, anything under here, it's just basically noise. We don't want to look at it. And by the way, the biggest bang for your buck always is the network, by the way. And yeah, so this is what an SBOB looks like. You can sign it, you can, all these typical things like cosign, full true, whatever, so that we have tamper-proofness. But now the question is, how do you create one? So the SBOB solves the problem of the false negatives. So we need to be able to have a contrast material that gives us the idea. So what does the application, here we have a Postgres, do normally? That's a database type. And what type of attacks or type of vulnerabilities here along the kill chain would I see if I executed it? And how dumb can I make my profile? So basically, how small, how many wildcards can I maximally put that I can still see the contrast to the different types of exploits or attack types, and I can have that as a contrast. So this is basically a deterministic algorithm that I let the agents execute per different application types. Like Postgres looks different, so different data, different application types look different, different languages look different. And here what I'm basically collecting is a huge library of test attacks and how they would look like and what signatures would show up. So again, so the SBOP is any point in time we look for this contrast to avoid false negatives. So if you write the SBOP wrong, it's something that you won't see. It's too coarse, basically. Right. Now, that brings us into the other part, which is Pixie. So let's say now that there is an anomaly. There is basically at any given point in time, we find such a violation. In this moment in time, at that node, we start writing immediately to a forensic database everything to make sure it's safe. But we also know that we've only caught the really loud signals. So what we now do is we say, let's go back 24 hours in the cache in time and ex post reconstruct all the protocol data that we've cached on each node. And this is what Pixie does. Pixie is actually a debugger in its original form. But if you compile it slightly differently, it can serve as the most effective way of keeping all that debugging data. And debugging data is the thing where you find all the nasty stuff. And we have 24 hours of history there. That means we can now lazily reconstruct what actually happened. And I'm going to give you an example with some very famous CVEs. This is actually, yeah, and we've upstreamed this now. There's even a graphical interface in Pixie now that you can export these things. So yeah, and now we're going to look at one of the most famous things that happened, most scary things that happened in the Java world in 21, I think, was Log4j. Because I hope that you remember that. So now it's attack time, first time. So I use this one as a calibration signal because everybody knows it and it's super well known. And we also have, it's a relatively complex attack. So we have an ingress server, there is a Shindy string that gets delivered, then this vulnerable Java library, the Log4j library, loads that string, downloads from external a jar file. That jar file allows you to drop into a shell, and then you've got remote code execution that's somewhere here. And in this particular case, just so that we have many parts, we use it to grab data from Postgres, use the Postgres data, and exfiltrate it via DNS. So this is just that we have the whole chain, and we can basically calibrate. We see all these parts over different protocols. Right? We have HTTP, we have pSQL, we have, this is a process tree violation, and here we have a DNS, get enter the DNS protocol. So basically the calibration signal that if I don't see it, then I need to tell the agents debug this because it's my agents that actually run this. Now, this is the complete, and Zurich told me this is the diagram that nobody understands. So I shall go through it slowly. So this is made for data centers. So we have one UI, and the UI only renders the data if you actually query it. The UI itself is, apart from cache, stateless. The data is always entirely on your nodes individually, unless it's been written to the forensic database. And here in the middle, magic happens here. We shall ignore this for now. So here we have a lot of daemon sets. And in this case, we chose to connect one cluster to it. We could connect many clusters to one UI. And we say we have two nodes. And on this one node, we put our wonderful Java service, the Postgres, the Nginx, etc. And we're going to simply say, what am I looking for? What do I always need to detect? And this is what you see here, the detection engineer's wet dream. This is the process, yes. This is an SBOP violation here, very, very, very bright, because we have unexpected process, a shell. It doesn't get as brighter than this. And also, the cool thing is we have here, and this is the wonderful thing about doing this in the kernel, we see the entire thing I just told you. We have Java doing some stuff with that jar file. Then it drops into a dash. Then there is a pSQL thing that selects from the database. Base 62 encodes the stuff it gets back and exfiltrates it to the evil. So this is where actually the stuff gets encoded, right? And it goes out via DNS because DNS is typically the easiest way to exfiltrate if you don't know much about firewalls. So again, this is as clear as it gets. Typically, unfortunately, attacks don't look like this. But yeah, this is the power of eBPF. If you have a process tree violation, you can ideally see everything, ideally. And now let's look what we would have seen in Pixie, right? That was just a process tree, but we have 10 different dimensions in the kernel that we can look at. We don't just have the process. We can also go anything over socket in this case. So first thing is, which ports were actually opened? And bytes went over them. Because sometimes the protocol inference doesn't work, or they get misattributed. So this is the first thing you look at, like which ports were even bigger. And then in this case, we can tap into HTTPS. This is also cool with the eBPF, right? You can resolve before and after the encryption. So we're not decrypting, but we're just intercepting the traffic in clear text. Here we should see that is the wonderful, very, very, very famous IOC for Log4j. And then we can also see it in the DNS. And I don't have time why P-SQL was omitted, but if you want to know why I don't use AI, ask me why P-SQL was omitted. Now, so this was basically, this is what we're looking for to actually prove that the attack happened. Now what we're going to do is, how about we have 3 attacks at the same time over 2 nodes, and we want to confuse it. Can we still detect the things and tell them apart? This is called the attribution problem. So in this case, and I won't tell you too much about what these CVEs or attack types really do because of time. So we got our Java back, our calibration signal, but we also have Argo CD. Argo CD often has these path traversal problems, a malicious render. You render a Helm chart or a customize, and then it can do way too much. In this case, you can grab secrets and steal it and deploy stuff with it. And we're deploying, in fact, React to Shell. That was is a similar, in a way, to the Java problem, but it let's say the attack gets delivered in a very, very different way. So we have 2 remote code execution types, and in fact, React to Shell will deploy the malicious render to Argo, and they are sitting on different nodes. Now, our identification is all local on the nodes, and the question here is, can we actually make a connection? And how would that work? How do we actually connect them? And now at this point, I have this graphically rendered. So what happens now, so we again have the these process tree identifications from earlier for each of these things. The only thing is that Argo, for example, has a much less identifiable signal. And in this case, what I did is I asked Pixie, well, how about we connect each socket to all the other sockets that ever happened in those 24 hours before, which of them actually connect, and which protocols were connecting them. And this is basically what the algorithm does. It's a Bayesian state machine, so we have priors and anteriors, and we have a cost function to basically say, what is the likelihood of this protocol giving me evidence? So think about me going to the doctor with a headache. Right? So maybe the doctor could ask me, did you drink too much beer last night? And I can say, well, if I say yes, then we know there's probably a reason for your headache. But I could say no, and then there are 2 options, right? I could not have drunk too much beer, or I could have drunk so much beer that I forgot that I drank the beer. And that is sometimes the problem. The non-existence of evidence doesn't necessarily rule anything out, right? And this is why you always have to cross-correlate various of these signals, and also you never know if you're actually right. So there's no 100% proof. The only thing is you can correlate all the stuff that is likely, and then you export it, and that's your likelihood of what really happened. And we can grab all these trees and reconstruct them lazily, and that's the idea here. So now I told you about that we're going to be talking about noise, and yes. Yeah, so for now, what I showed you was there was no noise on this on the cluster. But in a real life, you have a lot of traffic going on, right? And the misattribution I showed you earlier often happens that either your algorithm it just fails because it runs out of memory, out of CPU. But the other problem is that it can just get really confused. And yeah, by the way, I hope I said it. I'm not criticizing any of the other ways of securing and hardening your cluster. I assume that you've done everything already, right? And now we're putting noise on this, and I'm going to skip that one. And this is what actually a graph looks like if you model with K6S or other ways of generating traffic. Um, and if you especially ask the noise generator to mimic attacks that look like individual indicators of compromise. For example, you inject a Chindi string from log4j, but you don't do anything with it. Because this is the problem, for example, with AI, it will get the heck confused. In this case, what I wanted to know is how fast can I actually do this? How fast can I go through thousands of these rows of noise? And this is, again, this is a 150 seconds window. So you just imagine you do this for a year. How fast can I de-confuse this? And so I stole the, yeah. So when there's something strange in the neighboring pod, I'm not gonna, yeah. So one thing to bust the noise is one thing is graphical. This still happens, so especially if you're debugging for humans, if you have the time to look at it, the different graphical representation matters a lot from that earlier display, right, with this one. So this is something, and I love to do this for humans, right, to reduce the alert fatigue, is give them views like this way, the contrast might be better. But this hasn't changed the data, this hasn't gotten rid of the noise, right? So now the question is, how do you, okay, what happens under the noise? And the first thing is the noise matters. So how you model the noise is very, very distinct of how you confuse the algorithm. Let's look, for example, here on the right side, I did attack confusion noise. So this is basically, I put about 10,000 lookalike attacks that somewhat got stuck in the middle where there is one real attack in the thing. And this is a stress test basically to check if this algorithm will kill the other pods, right? This would be pretty bad if our security detection were to evict things or, and what we see here that about, yeah, for about half of them, we can still detect and then it gives up pretty much. At this point, you probably still saw that something was wrong. So, and we also saw that the time to verdict, and this is important, especially also if you think about doing this with AI, this time to verdict means looking at all the evidence and figuring out was this relevant or not. We're still in the 200 millisecond range, even under extreme confusion noise. So we start losing signal, we start dropping the actual throughput, but we can still, for those that are not dropped, we can still be in the millisecond range. And workup, that is basically the question of consulting each piece of evidence. So that's like measure my temperature, like to get the medical equivalent. We're still in the single millisecond range. And that's important because that means I can afford a lot of these checks, right? And that's something that, again, doing inference here, you would never be in that range to be even affording that pod to pod hop and reconstructing lazily because it's just that cheap. And it gets a lot better if I don't use noise that looks like an attack 10,000 times per 150 seconds. But in fact, if I use more realistic noise that has real traffic in there, then it starts like I'm not actually dropping anything. I'm, in this case, the time to verdict is a bit lower. And this is actually because I need to reconstruct all of these pod-to-pod hops in total during the same time window. And still, otherwise, the queries here, this means I have to query the entire history of these protocols, is still in a very acceptable range. So while I don't want you to take away exact numbers, just order of magnitude, to remember, and this is a feasibility study for the Austrian Armed Services. They wanted to know how, what is the ideal state? Where can we get down here? And again, here, is it robust enough to run this on mission critical stuff, or is it going to kill other the actual applications that are running? So, and this is, and what you should see, why do I call it Noisebusters, right? Because even under such extreme noise conditions, I can still, well, here identify half, and here identify everything for those 3 attacks that happen at the same time under noise conditions. And now let's look at the rules, and this is a bit more human readable, I hope. So you also see how I model the different rules differently. So basically, here I'm stealing a lot of secrets. That seems to be very confusing. And I'm using a lot of egress traffic. because that tends to be very expensive, because that means when I have to reconstruct the entire network graph. So that's expensive. So that's why we get this drops. Whereas if I model the noise differently, I have also a lot of secret stealing, but a lot more launches of processes dropping into shells or dropping binaries into the things, which are much, much brighter to identify, then I can reconstruct better. But still, just look at the numbers per 150 seconds. That's not particularly, well, if that's what happens to your cluster, you've got a serious problem, right? So this is a stress test, right, just to say. And the idea is to get rid of the noise under very adverse conditions, and how fast could it possibly work? And yeah, the other thing that I just want to highlight is this is a deterministic algorithm, but it's still statistical, right? Bayesian statistics is still very sensitive of how you model those weights. It's also weights, just kind of different ones. So here, for example, if you look at it for a while, so this is all Argo. Argo, like React should be here. Yeah, React is talking to the kid's API server, and then it's doing something with Argo. So that is that pivot via the API server here. But then what you see here, that it's connecting to log4j. That's nonsense. That is the algorithm classically confusing. It's saying, okay, this is red, the log4j, but it's confusing that this network was connected to this. And this actually changes with different noise levels. So I still have to be very, very careful in modeling this noise very correctly to get those Bayesian weights correct, because that's exactly what happens otherwise, is that the attribution is wrong. But so wrong attribution is something a human could still override. Now let's look at the other question. Yes, and I have no more time left. And one sec. Can we reduce data volume? And what orders of magnitude are we talking about? Again, this is anecdotal for now. I will present it in Vienna in September, the actual numbers, when I'm there. Look at one thing. For each identification, we need order of 10 such records, 10 pieces of evidence consulted. Think about that as one JSON document. And if we measure what is in HTTP DNS and just those socket connection stats during the 150 seconds, and how much I can, well, currently the adaptive writing reduces it by this factor, but this would be the ideal state that we would be reducing it to, right? Or depending what the customer also wants to see, if they want to also see attempted files. So currently, including the attempted attacks, this is the reduction, and this is significant. Even though this was literally 2 months of work that we've done. So that this is the scale of the work for now, right? And this is what makes me so passionate about, and why I call it digitally sovereign, because it means you can really move it to your own node in your own data center, and you don't have to ship it. No criticism against -0, Dynatrace, Datadog, anyone, but you trust them, right, when you ship your data to them. And this means you can keep it in-house. And with that, we had vertical course filters, hopefully within a couple of hundreds of YAML lines. They have to be tuned for contrast. They help you against false negatives. If you do them wrong, you don't see things. And then we have this backward-looking lazy resolution. That helps us against the whole false positives problem. Data volume reduction numbers is a work in progress. And the Cubescape is actually now merged. And if you want to contribute, here's the big ask, is one thing. I think I've asked you already for help me with realistic Java apps for doing the extension to the stack trace. The stack trace currently not consulted yet because I'm not an application developer. And the other thing, that whenever you find a good write-up of an attack that I can mimic and put it into my automatic attack contrast program, write it to me. You know, you find a blog post or you find a really nice thingy, just drop me up, whatever DM, and then I don't have to search for them myself. And with that, again, huge thanks for being here today, and whatever. Yeah.
Any questions? We only have one question. No. Okay, thanks, Ege.
Thank you.